Thanks a lot for taking the initiative to launch this series of seminars. Yes, as Otto already said, I will talk about the DMFT description of photodoped MOT systems. This is work done over the last 10 years, mainly in collaboration with Martin Eckstein, Denis Goles, Yuta Murakami, Jiachun Lee, and Sujay Ray. And the motivation is that we are interested in the possibility of tuning material properties by external laser driving, and one of the simplest realizations of that is the ultra-fast insulator metal transition induced by photodoping of MOT insulators. As you may know, interesting quantum states may emerge if we dope charge carriers into MOT systems by chemical substitution. Here is a sketch of the phase diagram of cuprates, and so one may ask what is happening if we introduce charge carriers by photoexcitation across a MOT gap or a charge transfer gap. From the theoretical point of view, this is a difficult problem for several reasons. One is that we are dealing with strongly interacting many-particle systems, which are already difficult to treat in equilibrium, as you know. The other is that these laser pulses, which we use to excite the system, are typically very strong, so we have to go beyond the perturbative regime. And the third reason, which makes this problem very difficult, is that often very different timescales emerge in the evolution of photodoped strongly correlated systems. This is illustrated in this sketch here, which shows that the excitation takes place on the timescale of the electronic hopping, which is typically femtoseconds in correlated solids. And then if the laser pulse has many cycles, the system can switch transiently into a so-called Floquet state, which may have properties very different from those of the equilibrium system. And then after the end of the pulse, a relaxation process sets in, but this often proceeds in several stages, where, for example, the system is first trapped in a so-called pre-thermalized state. If the system has long-range order, there can be slowdowns associated with non-thermal fixed points, and often the thermalization process then occurs on timescales which are orders of magnitude longer than the timescales needed to describe the excitation process, and so bridging these timescales in a numerical calculation is very challenging. So we have worked on the dynamical mean field approach, where one maps lattice model to a quantum impurity model as sketched here. So we focus on one of the sites that becomes our impurity site, and the rest of the lattice is replaced by a bath of non-interacting electrons, and the properties of this bath are then optimized to mimic the lattice environment. And often we work in an action formulation where the bath is integrated out and replaced by the so-called hybridization function, which plays the role of the dynamical mean field. Now, this formalism can be directly applied to non-equilibrium problems, as was first shown by Friedrichs and co-workers. Basically, all the steps in the self-consistency loop remain exactly the same, and in particular, we can still do this mapping from lattice problem to single-site effective models. The only difference is that these functions, the hybridization function, the Green's function, the self-energy, these are now functions defined on a so-called Kadanoff-Beim or Keldysh contour, and they are typically functions of two separate time arguments and not just a function of the time differences as in equilibrium, because we generically lose the time translation invariance in a non-equilibrium state. But apart from this, the steps in the DMFT loop are exactly those which you know from equilibrium calculations. Let me briefly explain how the electric field excitation enters into this calculation. We typically use a gauge with a pure vector potential where the field is given by the time derivative of the vector potential, and then in the kind of long wavelength limit, one can introduce the field by the so-called Pyle substitution, where the dispersion epsilon of k is shifted by this time-dependent vector potential. And the only place where the dispersion enters is in this step here, where we calculate the lattice Green's function from the local DMFT self-energy. And yeah, so the only thing that needs to be changed in the presence of an electric field is to take into account this time-dependent shift of the dispersion. So this is quite easy to implement. So now let us discuss more specifically photodoped Mott insulators and the different stages in the excitation and relaxation dynamics of such systems. We start in an equilibrium state where we have a filled lower Hubbard band and an empty upper Hubbard band, and then we apply a laser pulse with a frequency comparable to the Mott gap or the interaction U, and this will create doubly occupied sites or doublons and empty sites or holons in this system. And initially these doublons and holons have a very broad energy distribution within the Hubbard bands. And then on very long time scales, exponentially long in the interaction U, according to theoretical calculations, one expects that this system will thermalize, which comes with some adjustment in the density of these doublons and holons. But because this timescale can be very long in the presence of a large interaction U, what can happen on intermediate timescales, especially if there are couplings to bosons such as spins, phonons, or plasmons, is some relaxation into a pre-thermalized state where the charge carriers cool down within the Hubbard bands and the spectral weight starts to accumulate near the edges of the Hubbard band. And there is an interesting feedback between this pre-thermalization physics and the thermalization processes, in the sense that the changes in the, for example, spectral function in this pre-thermalized state have an effect on the thermalization dynamics, and vice versa, the energy released or absorbed during this thermalization process feeds back onto the properties of this pre-thermalized state, as we will see in the next slides. But first, let us show how this thermalization dynamics shows up in non-equilibrium DMFT calculations. And this was in fact one of the first problems which Martin studied when we implemented non-equilibrium DMFT with strong coupling impurity solvers. So the question, how does a photodoped Mott system thermalize? Here's the shape of the pulse excitation, a few cycle electric field pulse. And on the right-hand side, you can see how the double occupation goes up during the pulse. And then there is a slow approach of the double occupation towards the thermal value. And in this case, thermalization is actually associated with an increase in the doublon population, as you can see here. Anyhow, we can now subtract the thermal value and plot the difference between the time evolving double occupation and the thermal value on a logarithmic scale. And then you can see that deep in the Mott regime, and U equals 5, the thermalization is very slow, basically not visible on the time scale of this plot. But then as we approach towards the metal insulator crossover regime, this relaxation becomes faster and faster, and eventually in the crossover regime there's a qualitatively different evolution because basically the gap starts to fill in after the photoexcitation. But inside the Mott regime, we can now extract the thermalization time from these exponential curves. And if we plot this thermalization time as a function of the interaction, this shows this exponential increase, which was already predicted based on some theoretical considerations. Now, what this shows is that if we have a large U, a large Mott gap, then this thermalization time can be very long, picoseconds easily. And so one can ask what will happen now in such a system on shorter time scales, especially if we have scattering with other degrees of freedom, for example, phonons, spins, and so forth. So let's first discuss the phonon scattering. This can be studied in the Holstein-Hubbard model, where charge fluctuations coupled to dispersionless phonons with a frequency omega 0, and the electron-phonon coupling strength is expressed by G. What we calculated here is the evolution of the photodoped spectral weight within the region of the upper Hubbard band for different phonon coupling strengths. So this lambda here is a parameter which parameterizes the effective phonon coupling strength. And the gray box here shows more or less the energy region corresponding to the upper Hubbard band. So you see that the photodoping pulse here inserts doublons at the upper edge of this Hubbard band, and then as a result of the electron-phonon coupling, the electrons lose kinetic energy and they drift towards the lower edge of the Hubbard band. And this is a slow process in the presence of a weak electron-phonon coupling, but it is very fast in the presence of a strong electron-phonon coupling. In this case, you see that very quickly after the pulse, the energy, kinetic energy is dissipated and the doublons accumulate at the lower edge of the Hubbard band. So this is an example where the phonons act like a heat bath, so they absorb the excess kinetic energy of the doublons and the holons. However, if the phonon coupling is very strong, there can be a non-trivial feedback now from the excited lattice onto the electronic states, and this can affect the thermalization dynamics. And I will demonstrate this again with calculations for the Holstein-Hubbard model, and I will illustrate this effect by comparing the result to the pure Hubbard model without electron-phonon coupling. What is shown on the left side is the spectral function of the pure Hubbard model without phonon coupling during and after a photodoping process. And you can see that during the pulse excitation, there's a narrowing of the Hubbard bands. This is a field-induced localization effect. But after the pulse, there's basically no change to the spectral function, even though we have substantially photodoped the system by this pulse. In contrast, in the case where we have a strong electron-phonon coupling, there's a big change in the spectral function during and after the pulse. Here I have chosen an artificially large phonon coupling so that the Hubbard bands already in equilibrium split up into narrow polaronic sidebands. And now you can see that during the pulse, a whole series of additional polaronic sidebands appears, which fills the gap region. And the presence of these additional sidebands now has a significant effect on the lifetime of the photodoped carriers and their recombination dynamics. And this can be seen in this plot, which shows the evolution of the double occupation for different pulse amplitudes. So in the pure Hubbard model, you see that the lifetime of the doublons is very large, much longer than the timescales covered in this figure, and that independent of the photodoping concentration. Whereas in the Holstein-Hubbard model, because of this feedback between the excited lattice and the electronic states, we can see that for strong photodoping concentrations, if we generate a lot of these in-gap states, the lifetime of the doublons becomes very short, and we have a very fast recombination because now the doublons and holes can kind of bridge the gap by jumping between these phonon sideband states. Now, another type of bosonic excitation, which is relevant, is the electron-plasmon excitation. This can be studied in models with non-local Coulomb interactions, such as the UV-Hubbard model, which has a local interaction U and a non-local interaction V. This physics can be studied using so-called extended DMFT, which still maps a lattice model with local and non-local interactions onto a single-site effective model. But this model now has two dynamical mean fields, the hybridization function and a retarded interaction. So there are two coupled self-consistency loops a fermionic loop which connects the Green's function and the self-energy, and which fixes the hybridization function. And there's a second loop which connects the screened interaction and the polarization and fixes this retarded impurity interaction. Here's a result from a Dennis study of the photodiode MOT system using DMFT. In equilibrium, the imaginary part of the screened interaction has a single peak at the energy omega equal to U, so equal to the MOT gap. And this shows that in the MOT insulator, we have basically screening transitions associated with excitations across the charge gap or the MOT gap. So there's one screening mode associated with excitations across the MOT gap. And this leads in the real part of the screened interaction to a reduction in W at frequencies below the interaction U. But because screening in a MOT insulator is not very effective, this reduction is not very large. However, as soon as we photodope such a system, you can see that a low energy screening mode starts to appear. And this low energy screening mode grows as we photodope more and more charge carriers into the system. And this mode appears because in a photodoped MOT system, the doublons and holons can now produce low energy charge excitations, and that leads to this additional screening mode. And this has a significant effect on the screened interaction at low frequencies. So there's a reduction now in the W at low frequencies because of this metallization of the MOT state. This has consequences. For example, the MOT gap almost instantaneously shrinks because of this additional screening of the Coulomb interaction that is shown here. And the second effect is that the spectrum broadens, as you can see here. And this broadening is coming from these plasmonic kind of side bands which appear at high energies. One may then ask how this affects the lifetimes of the doublons and holons. And here is how the increase of the non-local interaction or the electron-plasmon coupling changes the lifetime. And you can see it very dramatically reduces the lifetime. And there are two contributions to this effect. One is the shrinking of the MOT gap. This more or less accounts for this reduction here indicated by the dashed line, but the biggest reduction actually comes from this electron-plasmon coupling, the possibility to emit plasmons, which are high energy excitations, and that then makes it possible to more easily recombine the doublons and the holons. Now the extended DMFT formalism can be naturally combined with the GW method. This was proposed 20 years ago by Biermann, Ariasetto, and George. And basically the idea is to take the local self-energy and the local polarization from extended DMFT and to take the non-local polarizations and self-energies from GW. And it turns out that in this GW plus DMFT method, the effective electron-plasmon coupling is even stronger than in eDMFT. And this can lead to quite non-trivial transient effects after a photoexcitation, for example, to a self-sustained population inversion after a strong photoexcitation. And this is shown here in this calculation also by Dennis for the photodoped single band UV Hubbard model. What is plotted here is the change in the kinetic energy after photoexcitation in a model with small v or small electron-plasmon coupling and in a model with large V or large electron-plasmon coupling. And in the weak coupling case, you can see that the kinetic energy goes down after the photoexcitation because the charge carriers relax within the Hubbard bands and accumulate at the lower edge of the band, as one naively expects. But for very strong electron-plasmon coupling, we have this very unusual behavior that the kinetic energy continues to increase after the photoexcitation, and this is because a population inversion starts to build up in the system, and the charge carriers now start to accumulate at the upper edge of the Hubbard band. And this comes from this strong feedback between the thermalization process and this transient metastable state, namely the energy which is released from this plasmon-enhanced double-Holland recombination. This energy flows to the kinetic energy of the remaining charge carriers, and that leads to the increase of the kinetic energy that you see here and to this transient population inversion. And that would be seen, for example, in electron loss spectra. Here we plot the equilibrium electron loss spectrum, which has a positive, say, spectral weight at energies larger than the Mott gap, but after the photoexcitation, some negative spectral weight appears because there can be now energy gain in these scattering processes because of the inversion of the population. Now, GW plus DMFT is very interesting for realistic material simulations. We have implemented this over the last years on the equilibrium side with quite some success. And what this requires is a multi-scale approach where we perform a single-shot GW calculation in a large energy window and then self-consistent GW in some intermediate space and eDMFT only in a small subset of the most strongly correlated orbitals. This has not yet been done in non-equilibrium, but what Dennis has done is calculation for the DP model of cuprates. This basically corresponds to the blue and the red box in these calculations. Or more specifically, in this calculation, we treated both the P and the D states within GW, and we added local self-energy and polarization corrections from the D states. And what you see here are the photoemission spectra of the P and D states. In black, the equilibrium spectra, and the colored lines show the spectra after a photoexcitation. And there are two effects which one can find in these calculations. One effect is a relative shift between the P and the D states. This is a Hartree shift coming from the reshuffling of charge between the different orbitals. And the second effect is this broadening of the Hubbard bands due to this electron-plasmon coupling. Now, let me come back in the last minutes to another important cooling mechanism, which can lead to interesting metastable states. That is the electron-spin interactions, which can be very strong in an antiferromagnetically ordered system or in a system with strong short-range antiferromagnetic correlations. In this case, a hole which is injected into such an insulator will flip spins against their antiferromagnetic alignment with each hopping. And so each of these broken bonds costs an energy proportional to the exchange coupling, which is quite substantial. So after just a few hoppings, this hole will lose its kinetic energy. And so we end up in a cold photodoped state. And this is shown here in this simulation, where I plot the evolution of the photodoped population within the region of the Hubbard band for a weak photodoping pulse in an antiferromagnetic insulator. And in this case, the pulse is so weak that the antiferromagnetic order survives this pulse. And so the cooling mechanism, which I have just described, is active and leads to the very rapid cooling of the photodoped carriers that you can see here. On the other hand, if I apply a much stronger pulse, the antiferromagnetic order melts and then this cooling mechanism disappears. Anyhow, so we have now seen that there are various mechanisms, electron-boson coupling mechanisms, which can lead to a cooling of photodoped carriers. So this raises then interesting questions about potential electronic orders which may emerge in photodoped MOT systems, where the intraband cooling leads to a metastable long-lived state, which has cold photodoped doublons and holons. For example, one may ask if some kind of condensation of these doublons and holons can occur in such MOT insulators. And that was already addressed by Roche and co-workers in the cold atom context quite some time ago. What he showed is that if one has a large U Hubbard model and a very strong population inversion, basically only doublons and only holons, then such a system at effective temperature 0 should show so-called eta pairing, which is a superconducting state with a staggered order parameter. So the usual S-wave superconducting state, for example, in the attractive Hubbard model, has an order parameter which has the same value on each lattice side, but this eta pairing state, which was predicted for this photodoped MOT system, has a staggered order parameter. And this can be also found in non-equilibrium DMFT calculations. Here's an example where we photoexcite very strongly a MOT insulator, and we apply a clever pulse, which results in a sufficiently cold photodoped population. And in this case, the eta pairing order parameter indeed grows during the application of the pulse, and then after the pulse, it is conserved. And then we can explore the properties of this eta pairing state. For example, we can apply a half cycle field pulse to this system to accelerate the charge carriers, and then one finds that the current does not decay after such a half cycle pulse, and that's an indication that this is a superconducting state. Martin and Chachun have studied this problem using a so-called steady state DMFT approach, where one couples a full electron bath to the upper Hubbard band and an empty one to the lower Hubbard band, and with this one can control the photodoping concentration and also the temperature of the charge carriers to some extent. And what they showed is that this eta pairing phase is actually a very robust phase, which extends over a wide region of doublon concentration. So it doesn't only exist in the extreme photodoping limit that was discussed by Roche and co-workers, but it is a very robust phase which should exist for various photodopings at sufficiently low effective temperatures. They also calculated the optical conductivity, whose real and imaginary part is shown here. I want to point out two aspects. One is that the real part of the conductivity can be negative in the energy region corresponding to the Hubbard bands, because we have this population inversion in the system, so there can be energy gain at this in this energy region. The second point I want to stress is that generically we do not have a gap in this state, even though it is superconducting. So in contrast to a S-wave equilibrium superconductor, there's no gap. And that comes from the fact that in addition to these condensed doublons and holons, there are non-condensed singly occupied sites. And so we should think of the eta pairing state in terms of a two-fluid picture where condensed doublons and holons coexist with normal singlons. Now, eta pairing with its staggered order parameter is naturally found on bipartite lattices. One may ask what happens on a geometrically frustrated lattice, such as the triangular lattice Hubbard model. For example, one may ask, is there something analogous to the 120-degree order that one expects in spin systems? And indeed, using various types of numerical calculations, we argued that there is a 120-degree condensate forming on this triangular lattice, where the order parameter switches by, or the phase of the order parameter switches by 120 degrees between the green, blue, and red sublattices. And that is a very interesting superconducting state, because the phase twist between these sublattices leads to persistent currents which run along these bonds, and that breaks inversion and time reversal symmetry. So this photodoped superconducting state is actually a chiral superconducting state. And finally, let me mention that in multi-orbital systems, we can also find interesting variants of eta pairing, namely orbital singlet, spin triplet type of eta pairing, where we have a staggered version of this triplet superconductivity, and that is found in the very strongly photodoped 2-orbital model with positive Hund coupling. And with this, my time is up. So let me summarize. I discussed non-equilibrium states in photodoped Mott insulators and discussed the thermalization dynamics and the relaxation into a pre-thermalized state by various types of electron boson coupling mechanisms. And since these pre-thermalized states can be long-lived in the presence of a large gap, this is an interesting playground to search for non-thermal electronic orbits, for example, for non-thermal superconducting states such as eta pairing. And if you are interested in this topic, please have a look at this preprint of some review article which we have been writing. This covers not only DMFT results, but more broadly numerical and analytical results for photodoped Mott systems. So if you feel that some citations are missing or some discussions are incomplete, please let us know. And if you are more specifically interested in non-equilibrium DMFT, I point you to this almost 10-year-old review article, which is still, I think, a very good reference for this topic. And with this, I stop and thank you for your attention.
Okay, thank you, Philipp. Thank you for taking the time to prepare such a broad overview, and it's remarkable to see how the field of non-equilibrium DMFT has expanded and progressed. So now the talk is open for questions. Go ahead.
Yes.
Hi. Very nice talk. I have one
Can you introduce yourself?
Hi, I'm Dr. Irakli Titouinidze from Hamburg. So I want to ask one question. You show in several plots some parameters which was linearly increasing in time. Do at some point they saturate, or they continue increasing in time with further?
You mean this population inversion result?
For example, or zero? Yeah, exactly. For example, this plot. Yeah.
Oh, yeah, of course it will saturate at some point. Yeah, I mean,
how long does it take, and if it is possible to capture it with time evolution DMFT, because I know that at some point it may come some problem if you do not attack directly steady state.
Yeah, I have to clarify that this is only a transient state. So this inverted state only exists as long as double-Holon recombination processes kind of inject energy into the remaining doublons and holons. And once this recombination process stops, this inversion will start to collapse. And yeah, so it's only a transient state. And on longer time scales, you would see a decrease again of the population. But here, with the techniques we had available at the time, we were not able to simulate to long enough times to actually show this.
Okay, and up to what times you are able to simulate your calculation? It's more or less what you show here, or it's slightly longer?
Well, I mean, there has been quite a bit of progress in this area. On the one hand, one can nowadays use truncations, memory truncations, which cut off the memory time in the self-energy, for example. And that has been shown to allow us to go to far longer times, maybe 100 times longer times. And also Dennis and co-workers have developed memory compression techniques, which allow to push these simulations to much longer times. So yeah, I mean, with the techniques that we had available 6 years ago, that was roughly the limit. But nowadays, if one uses the latest available technology, I think one can push such calculations to 10 or 100 times longer simulation times. So then one might, depending on the gap size, start to see how the thermalization dynamics sets in.
Okay, thank you very much.
Pasha, do you want to ask a question?
Yeah, so in fact, it's exactly the similar plot. So Philipp, So do you find this similar effect in eDMFT just without GW? Because you know, I'm a little bit scared, worried about this combination where you put two self-energy together, which you know, there is some recent discussions that it may be not causal and so on and so forth.
No, I think it's not an artifact. I mean, it requires a very strong electron boson coupling. We have found similar effects in a electron phonon coupled model, a so-called Hirsch type model. If you choose a strong electron phonon coupling parameter in this model, you find similar phenomena. So I think what GW plus eDMFT does is it gives us effectively very strong electron plasmon coupling, which is much stronger than what we find in pure eDMFT. And I think that is what we need to get this effect.
Maybe additional question, if I'm allowed, about this electron magnon scattering in this Keldysh formalism. I remember you also did some cluster calculation, cluster DMFT.
Yes.
If you can describe this effect in cluster, or you need really big light?
You mean this cooling effect here?
Yes.
This cooling effect does not require long-range order. So if you have short-range antiferromagnetic correlations, that is enough. So Martin did some cluster or DCA calculations with 4-site clusters, and he showed that this cooling effect is very prominent already in these cluster calculations, even though we only have very short range order in these calculations. So that's
okay. Thanks.
Young, you want to ask a question?
Yeah. Thank you. I have actually a question in this slide. So, in this slide, you mentioned the fast slowing down of this holon or doublon. So, if I just looking at the single one and there are momentum, so if I understand correctly, there are momentum is vastly losing to the background, and how this AFM background have the momentum conservation work? Should I think about some many pairs so that the momentum is more or less conserved?
Well, yeah. You're asking what moment?
Yeah, so there is kinetic energy loss, so momentum should be go somewhere. So where is momentum?
Yeah, but this is DMFT. I mean, I think we anyhow make approximations at the level of momentum conservation. But so I think that that is just violated. But the main argument here is the loss of kinetic energy, which goes to these the breaking of these antiferromagnetic bonds here, and the exchange energy is not small in typical Mott insulators. So in practice, this hole is not very mobile. After a few hoppings, it is almost frozen inside this antiferromagnetic background. And that gives us this very rapid cooling effect here.
Yeah. Okay.
And actually, maybe I should say there's an even faster mechanism in multi-orbital systems. If we have Hund coupling, we can have flips from high spin to low spin states by the same type of hole or doublon diffusion. And the Hund coupling is, of course, even much larger than the exchange coupling. And so this is an even stronger and faster cooling mechanism than what I have explained here.
Okay, thank you. Next question would be by Luke.
Can you guys read it? Because I'm kind of walking on the street and it's difficult.
Yes.
I typed it.
Sure. So Luke wrote, it seems that most results can be interpreted in terms of population dynamics of the upper and lower Hubbard bands. Is there a case where the upper and lower Hubbard band picture breaks down?
Well, for example, if you have a small gap MOT insulator, then if you start to strongly photodope it, the MOT gap may actually close. I mean, the Hubbard bands may broaden and the MOT gap may be completely filled in, and then yeah, the pictures that I have described here are not valid anymore. Then we have very fast recombination processes like in a metallic system. So basically what I have described here is valid as long as the MOT gap survives the photoexcitation, if it's large enough that it doesn't get filled after the photoexcitation.
Great. Paul, do you want to ask your questions?
Sorry, now you should be able to hear me. I'm
Yes.
interested in, at some point, I think during the part about photodoping the superconducting state, you mentioned that you designed the pump in a way to leave a cold photodoped state. And I'm wondering, what exactly did you change with the pulse, and how did you engineer it to leave behind the cold state?
Mm-hmm. Yeah, that's an interesting topic. I didn't go into this. I didn't have time to go into it. But basically, what we showed in a series of papers is that if you have multiple bands, you can excite charge, say from a filled band to the upper Hubbard band, or from the lower Hubbard band to an empty band, and that this kind of charge transfer is associated with a strong transfer of entropy between your Hubbard band and this initially filled or empty band. So there's a very strong entropy cooling effect. And what we have exploited here is precisely this kind of entropy reshuffling from our Hubbard bands to some initially filled or empty bands. And that's how we achieve a photodoped state, which is effectively very cold. Yeah, so there's a bit of, yeah, it's not, we cannot achieve this with direct excitations between the lower Hubbard band and the upper Hubbard band. But if we have additional bands where we can dump entropy, then this can be achieved.
Thank you.
Eric,
sorry.
Sorry, we'll finish with you, Henri.
Okay. Natural. So can I
Okay,
speak?
no, go ahead, since Eric is not.
My question, of course, is what about experiments? What is the situation now with these pump probe experiments, which begin to be done very systematically? Is there any case in which the MOT state has been photoexcited?
Mm-hmm. Yeah.
Do you have cases which you can compare? Do they reach in a short enough time scale to be able to see the recombinations, etc.?
Yes, absolutely. Yes, I mean these photodoping studies, they were motivated in part by experiments which have been done since the beginning of 2000 or even the 90s, where people use short laser pulses to photodope MOT insulators, such as cuprates, for example. And then, yeah, I mean, at the time, maybe the resolution was 200 femtoseconds. It was a little bit difficult to see the faster processes, but they could clearly see the metallization of the system after the photodoping pulse and the appearance of in-gap states and so forth. And yes, nowadays the time resolution of such experiments is much better. It's a few femtoseconds, and so one can really start to directly compare these calculations with experiments. Of course, in experiments there are other phenomena which come in, for example, impurities and so forth, and that makes the story more complicated. But I think the basic phenomena which I've described here are all actually seen in experiments, and yeah. So in the review article which I mentioned at the end, we tried to connect a little bit to experiments, and we discussed to what extent the calculations and the theoretical understanding is compatible with experiments. No,
Did they really try with starting on the mud insulating state, because the mud state is in principle not so dirty.
Mm-hmm.
The cuprates become dirty when you dope them. But
yeah,
when,
that's right.
so
yeah, of course they were done on undoped cuprates. But still, they see some kind of in-gap states where it's not so clear. Is this now, are these excitonic states? Are these maybe polaronic states? Are these impurity trapped states? Yeah, as you know, it's complicated. One would really have to do material-specific simulations to address this, and this has not really been done yet.
Okay, thank you very much. We'll end with the last question by Eric.
Yes, I was wondering, so for all of this, usually impurity solvers are the bottleneck. Can you say a bit about the current status and maybe the near future of impurity solvers for non-equilibrium systems?
Yes. Yeah, you are right. I mean, all these calculations which I showed here were based on very simple non-crossing approximation type impurity solvers. They turn out to be quite appropriate for MOD systems. At least they seem to give qualitatively the correct results for MOD systems. What one can do is to go to higher orders, 1 crossing approximation, 2 crossing approximation, that I think would be, for most of the applications, almost exact, because these photodoped systems are in some sense hot, and so NCA type calculations have mainly problems at very low temperature. They cannot properly describe the Fermi liquid state, but at high temperature this is fine. So I think that would be good enough, but of course there have been very serious efforts by Guy Cohen, Emmanuel Goul, and these people, inchworm type methods, which provide really numerically exact solutions for at least single band problems. And I think right now, in collaboration with Martin, they are kind of implementing this for at least steady state problems. So that seems feasible. I don't know what is the status for multi-orbital systems, but yeah, I think for MOD states, I'm quite optimistic that with these techniques, and maybe even with just OCA or second order, third order strong coupling expansions, one can get quantitatively accurate results. When it comes to cluster impurity solvers and multi-orbital solvers, it is more challenging. There I don't right now see a very good solution in the near future. Of course, there are all these, I don't know, quasi-Monte Carlo and so forth techniques. If the effective perturbation orders turn out to be sufficiently low, then one can simply evaluate these integrals in strong coupling expansions exactly, and maybe go beyond third order easily. But for multi-orbital and cluster problems, I think one has to go substantially beyond these orders, and yeah, let's see. But for single-site problems, I think we almost now have the tools to do exact non-equilibrium DMFT calculations.